the black body radiation. So the issue was investigated using the laws of thermodynamics in the mid 1800s. And it was found that not just for the black body, but for any body that is in thermal equilibrium with radiation, it can be demonstrated using thermodynamics that the ratio between emissivity, eta, and the absorption power, alpha, is some function that depends on the temperature of the body and on the frequency. And this function is universal, meaning that apart from temperature and frequencies, that are the two variables, it depends only on universal constants like the speed of light or similar. This relation applies to any body in thermal equilibrium, but if we consider specifically the black body, by definition alpha is equal to 1. So eta becomes identical to k. So this function that is investigated for the case of the black body is emissivity. Obviously, if one integrates emissivity over all possible frequencies, what is found is a function that depends only on temperature, and it is given by the Stefan law that we already used in calculating the solar constant. That is that the integral of the emissivity of the black body is proportional to the fourth power of temperature, and the constant is the Stefan-Boltzmann constant. This applies to a black body, okay? For a body that is not a black body, instead of sigma, we would have sigma times another constant that depends on the body. In the electromagnetic theory, we can also introduce another important function, that is the spectral energy density. The spectral energy density of the radiation is by definition the energy per unit volume. This is why there is the term density in the definition, and per unit frequency. That is why there is the term spectral. So it is the energy of the electromagnetic field per unit volume per unit frequency. It is intuitive that there must be a relation between emissivity and spectral energy density, because the emissivity is the electromagnetic radiation emitted by a body. So if we go near the surface of a body and take a unit area and we measure the energy that crosses this unit area and consider the energy for each spectral component, so for each frequency, okay, this energy will fill a volume that is near the surface of the body, okay, so it will contribute to the spectral energy density. In equations, we have that emissivity is by definition the energy per unit area, time, and frequency. If we multiply both sides of this fraction by the speed of light, because we assume, of course, that we are in vacuum, in the denominator we have c times dt, but c times dt is the space dz, okay, in that the radiation goes through in the time dt. So you see that in the second form of the formula, you have dE over dx, dy, dz, that is the energy per unit volume, and then we divide by dνe. So the expression of emissivity suitably manipulated gives the result that eta is equal to c times u. In conclusion, for a black body, capital K is equal to eta, eta is equal to the product C times U. That means that we must calculate eventually the spectral energy density, okay, of the black body, and then we multiply it by U to obtain E. Why is all of this necessary? Because calculating U is relatively easy. We can do it by applying concept of thermodynamics and electromagnetic theory, okay, very easily, as we shall see. How can we produce a black body? We have a schematic representation of the black body that is shown in the next figure here. So consider a block of material so the block is the cubic contour, okay? And this block is kept at a fixed temperature T, okay? Then inside the block there is a cavity, so this sphere is empty, okay? And of course the walls, the spherical wall of the cavity radiates. It is able to emit electromagnetic radiation into vacuum and also to absorb electromagnetic radiation into vacuum. So you have, don't consider for the moment this hole on the right, okay? Assume that there is just a cavity, okay? So the cavity is eventually filled with radiation. And since the whole block of material is kept at a constant temperature, we expect that also the radiation inside will be in equilibrium with the block of material. So there will be no exchange, no net exchange of energy between the block of material and the radiation. Of course, for each elementary absorption or emission of radiation, there is an exchange of energy, but they balance each other. So at each position of the cavity, of the boundary of the cavity here, and at each instant of time, the amount of energy that is emitted from the body into the cavity is equal to the amount of energy that is absorbed by the body from the cavity, okay? If you place a thermometer suspended in the cavity like this little gray area, assume that this is a thermometer, okay? This thermometer will always show the temperature T because the thermometer will be subjected to the radiation field, okay? So it will also go into equilibrium with the radiation field. And it is shown that the temperature that is shown by the thermometer does not depend on the position of the thermometer inside the cavity and does not depend on the orientation in space of the thermometer inside the cavity. Okay. Then you want to measure the distribution of energy in the electromagnetic radiation. How can you do it? Well, you can open a little hole. So this one is a little hole, very little, so it does not perturb significantly the situation inside. And then you measure the energy. You put some equipment near the hole, and you measure the energy that is coming out. And you can place also, before the equipment, you can place a filter in order to detect one frequency at a time. So conceptually, you can perform the measurement in this way, and actually you can do it in this way. Obviously, if you open a hole, there also will be some radiation that will come in, as shown by these arrows, okay? So the radiation that comes in is compensated by the radiation that goes out, so there will be no significant change in the situation inside because the temperature is anyhow kept constant by the thermostat, okay? And if this radiation enters with some frequency, then eventually it will be absorbed by the walls and re-emitted, maybe in another frequency, and then absorbed and re-emitted, and eventually the distribution of the frequencies inside the cavity will be constant. Okay, so the issue is now how to measure that we just showed and how to calculate the spectral energy density of the black body. What do we get from the experiments? From the experiments, we get this behavior. So these curves show the spectral energy density that is measured in joule per second per cubic centimeter. As a function of frequency, you remember that we expect a universal law, so it must depend only on universal constant that we know yet, okay, but we should calculate them. And the two variables are frequency and temperature. So if we plot the curves as a function of frequency and we use temperature as parameter, we obtain this form of the curves. The temperatures correspond roughly to the temperature of the surface of the sun. It's about 6,000 Kelvin, as you remember, or other temperatures near it, okay? The important thing is that the curves have a peak, and that when you increase the temperature, the peak, the value of the peak increases, which is reasonable because more temperature means that you have injected more energy, okay? And also that when the temperature increases, the position of the peak with respect to frequency goes to the right. Okay, you see the three peaks move to the right at increasing temperatures, okay? If you look carefully near the origin, let me expand the figure. Near the origin, the curves look like parabolas, okay, but at some point they depart from parabolas, they reach a peak and they go down again, okay? But near the origin, they look like parabolas. How can we calculate the spectral energy density? The reasoning is as follows. We want to calculate the energy per unit volume and frequency. We try to split the problem into two blocks. The first block is we try to describe the electromagnetic field as a superposition of monochromatic waves. And this is something that can be done, as you know. So then we take an infinitesimal interval of frequency, dν, and calculate how many frequencies are there in the elementary interval. Okay, so how many frequencies belong to that interval. So we have the number of frequencies, or if you prefer, a number of modes, of electromagnetic modes, per unit frequency. Then we calculate separately the energy of each mode. So we have two ingredients, two factors, the energy of each mode and the number of modes per unit frequency. If we take the product, then we obtain the energy per unit frequency. Then we divide by the volume and we obtain the energy per unit volume and frequency that is exactly the spectral energy density. So now let's tackle the two blocks separately. We start by calculating the number of electromagnetic modes per unit frequency. One of the issues that can be demonstrated by thermodynamics is that the spectral energy density of the cavity does not depend on the form of the cavity. That means that for the calculation, we can take any form, and of course we select a form that is convenient, like a prismatic form. So we take a cavity of the prismatic form. So instead of a round cavity, we take a cavity of the prismatic form. And we take a prismatic cavity like a box in which the three sides of the box are called D1, D2, and D3. So the volume is, of course, the product of them. And we assume that D1 is aligned with the x-axis, D2 is aligned with the y-axis, and D3 is aligned with the z-axis. Okay. Then we know that the electromagnetic field in the cavity must be finite for physical reasons. Otherwise, we would have an infinite energy of the electromagnetic type inside the cavity. So we can expand the electromagnetic field into a Fourier series, okay? Of course, the Fourier series will replicate the field outside the box, but we don't care because we are considering the field only inside the box, okay? And this is a calculation that is trivial, okay? So the expansion is based on the wave vector, okay? The wave vector for the electromagnetic field is defined, as you can see in the first line, it is 2 pi times, and then we have n1 over d1. n1 is any integer, positive, 0, or negative. d1 is the side of the box on axis 1, and I1 is the unit vector of axis 1. Then we have the similar element for axis 2 and 3. So this is the definition of the wave vector associated to the individual frequency of the radiation in the Fourier expansion. The square modulus of it, of course, is 2 pi square times ni n1 square over d1 square, and so and so. Then we take the positive square root of k squared, and this will be k. And then, if you remember, if we multiply by the speed of light in vacuum, we obtain the angular frequency of the individual component, monochromatic component of the radiation, and it will be equal to 2 pi times the frequency. So each frequency is proportional to k, and k is the modulus of a vector whose definition is given here. Okay? And the electromagnetic field will be a superposition of modes, each mode with this frequency. Then we make another observation that if you take any vector k, and then you change any of the indices n1, n2, and 3 by 1 unit, you go to the next vector k. So this reasoning is exactly identical to the reasoning that we already performed in a completely different situation when we were discussing of the possible k vectors inside the Brillouin zone, okay? This is different. This is the electromagnetic theory, but the mathematical apparatus is identical, okay? So the k vectors are equally spaced, okay, in the k space, because you reach one vector from another vector by changing the indices by 1 unit at a time. That means that you can associate an elementary volume, it's not infinitesimal, it's small volume, to each k vector, that is to the tip of the k vector. And if you look at the first formula, this small volume will be 2 pi over d1 times 2 pi over d2 times 2 pi over d3, that is the variation of each coordinate of k when you change the index by 1 unit. So globally, this product is equal to 2 pi cubed divided by the volume of the box. Now you remember the goal of this part of the calculation is to find how many modes are present in the elementary interval of frequencies. Okay. But if you look at the expression of omega, omega is proportional to the frequency, and the frequency is proportional to k. So an elementary interval of frequency is proportional to an elementary interval of k. So changing the frequency by an infinitesimal is equivalent to changing k by an infinitesimal. However, k is a vector, whereas the k that appears in the expression of the frequency is the modulus of the vector, okay? So this vector can be oriented anywhere in space. So it defines a sphere, okay? So it is like having a fixed value of k that being the modulus of a vector can be oriented anywhere, okay? So this K defines a sphere of radius K in the K space. If you then change K by an infinitesimal amount, you increase by an infinitesimal amount the radius of the sphere. So you construct a shell whose thickness is dk. So it is in the next page, okay? You have the K space. So the axes are K1, K2, and K3. You start with a sphere, okay, of radius K. Then you increase the radius by a small quantity. So you have a shell. Now you want to know how many vectors K have the tip inside the shell. But you remember that each tip is associated with a small volume whose volume is 2 pi cube over V. Okay, so all these small volumes are uniquely associated to the tips of these vectors. So in order to know how many tips of these vectors are inside the shell, you just take the volume of the shell and then you divide by the volume of this little cube. And in this doing, you find the total number of cubes associated to the vectors whose tip is inside the shell. Okay. So now it is just a calculation. One thing that we must remember is that the electromagnetic field has a polarization. So for each K vector, there are two independent polarizations. So in order to find the total number, we must eventually multiply by 2. So a sphere of radius K has a volume that is 4 over 3 pi K cube. This is the volume of the sphere. We divide by the volume associated to the individual K vector, so we divide by 2 pi cube over V. And then we multiply by 2 because of polarization. So this gives you the number of modes that belong to the sphere. Okay? Now we convert the information from K into frequency. So we must adopt the relation that K is equal to 2 pi ni divided by C. So we simply make the replacement. And after some elimination of factors, we find 8 over 3 pi V times the cube of ni divided by C cube. This is the number of modes in the sphere. But we need the number of modes in the shell. So we must increase ni by an infinitesimal. So we take the derivative. When we take the derivative, the 3 here cancels the 3 in the denominator, and we are left with ni square. And then we want it per unit volume, so we divide by the volume of the box. So in conclusion, the first part of the calculation is this, relatively easy. The number of modes per unit frequency and volume is 8 pi n squared divided by the cube of the speed of light. Now we have to calculate the energy associated to each mode of each frequency. Okay, so essentially we have split the calculation into the first part, that is the one that is just concluded, and this part was uniquely based on the electromagnetic theory, so we are confident that it will work. Okay. The second part will be based essentially on thermodynamics. Okay, we try to calculate the average energy of the modes whose frequency is equal to n, and then we take the product. Okay, so people of 1800, of course, they were able to do such a calculation. They already had developed thermodynamics. Okay, and they knew that the distribution of energies of a system in equilibrium follows a distribution law that is the so-called Maxwell-Boltzmann distribution. Okay, so in order to complete the calculation, the only ingredient that they could avail themselves was the Boltzmann distribution. So let's do it. They said, let's treat each mode as a classical particle, okay? Because each mode can be described as an oscillator, as a linear harmonic oscillator, like the vibrational modes in a crystal, okay? The analysis describes the same type of result. So it is like the modes of the electromagnetic field are like little oscillators, okay? Assume that we have a bunch of these oscillators in equilibrium at a given temperature T, okay? So the classical thermodynamics explains how to calculate the so-called average occupation number at each energy, okay? This average occupation number is some capital P equal to a constant times exponential of minus beta E, in which beta is 1 over kBT, sorry, with kB the Boltzmann constant and T the temperature. Okay, so what is the meaning of this distribution law? Well, obviously, if you integrate all of this over energy, you find the total number of particles. So you find the normalization constant P0 if you know the total number of particles. So PE times an elementary interval of energy gives you the number of particles of the system whose energy belongs to the little interval d epsilon around the energy epsilon. Okay. When you have a distribution function, it is easy to calculate the averages of any function. So if you have another function alpha that depends on energy, and you want to calculate the average of alpha according to this distribution, what you do is you take alpha p, you integrate over energies, that is from 0 to infinity, and then you normalize to the integral of p, okay? On the other hand, it is immediate that apart from the multiplicative constant, the integral of p is equal to 1 over beta. Okay, so the average sorry, the integral of P is P0 divided by beta. This can be calculated immediately, okay? By the way, it is here. It is just in the next line, okay? Okay. So the average of any function alpha is equal to beta times this integral. For the problem that we must solve, what is of interest is the average energy, okay? So what we must calculate is the average energy of these oscillators. So alpha is energy itself, okay? So what we must do is to calculate this integral that is in the second line, in which we replace alpha with epsilon, that is the energy. So we must calculate this. And the calculation is immediate, okay? The average energy is just kT. So it is the parameter that appears in the exponent of the distribution function. So the average energy of the oscillators in the classical picture is equal to kT. At this point, the analysis is completed because we have to multiply kT. By the way, kT is a constant for each oscillation mode because it does not depend on the frequency. So kT is the same for each frequency of the oscillation mode. So we multiply kT by this quantity, 8 pi n squared over c cubed. And this is the conclusion. The average energy times the number of modes per unit frequency gives the spectral energy density of the black body according to this theory. That is, we find 8 pi kT over c cubed n squared, okay? You remember that we noticed that near the origin, the black body curves appeared like parabolas, like the square of frequency, okay? And this is correct. Indeed, this law that was derived by Rayleigh genes is correct at low frequencies, okay? Because you remember that in the black body radiation, the experiment showed that near the origin, the curves are like parabolas, okay? But unfortunately, if you go up in frequency, eventually a parabola diverges, okay? And if you try to integrate this formula with the frequency going from 0 to infinity, of course, you find infinity. And this was called the disaster, the catastrophe of the ultraviolet, okay, because the high frequencies correspond to the ultraviolet radiation, okay? So, of course, this formula is wrong. It is a good approximation at low frequency, but it doesn't work in general because it's visible. The integral of it would diverge, okay? The solution to the riddle was found by Planck, who changed the calculation of the average energy. It is not written in this page. So this page shows only the result of the calculation, okay? And the idea was that ascribing the same average energy kT to each frequency is too strong. It doesn't work, okay? Doesn't make any sense. We would expect that the average energy of the mode at some frequency should also depend on the frequency itself, okay? So the idea was, let's leave the electromagnetic part untouched. So the density of the modes will still be 8 pi ni squared over c cube. And let's change the average energy of the modes, and by heuristic considerations, Planck was able to find the correct result, okay? And the correct result is here. Instead of kT, let's use this more complicated expression. That is, the average energy of the mode depends on frequency, and the dependence is like h ni divided by the exponential of h ni over kT minus 1, in which the Planck constant appears, h, okay? So if you use this expression of the average energy of the mode instead of kT, you find this formula that is universally known as the Planck law, that was found in 1900. And this formula perfectly fits the experiments. So all the experimental curves of the black body are exactly described by this formula here, that, as you can see, contains frequency, temperature, and universal constant that are h, c, and kb. But also, we can see whether this formula becomes the Rayleigh and Jeans law at low frequency, and actually it does, because if you take a very small frequency, then the exponential becomes 1 plus the exponent. So you have 1 plus h ni over kT and then minus 1. So the 1 will kill the minus 1. H will kill h. Ni cube over ni will become ni squared, and then you have kT on top. So this has, as a limiting case, exactly the Rayleigh-Jeans law at small frequency. On the other hand, in order to deduce this expression, Planck was obliged to introduce an extra hypothesis. And the extra hypothesis was that the exchange of electromagnetic energy between the black body and the radiation field occurs only in integer multiples of the elementary energy h ni. So when there is an exchange of energy, according to this hypothesis, between the electromagnetic field and the black body, only integer blocks, only finite blocks of energy can be exchanged, and the minimum energy that can be exchanged is h ni. This in 1900 was an extra hypothesis. Okay, it was not justified by any other physical law. However, it worked very well. I think that in the next few pages there is the explanation. Qualitatively, if the energy can be exchanged only in finite blocks, then one cannot perform anymore the integrations, because performing integrations imply infinitesimal amounts of energy. So assuming that energy can be exchanged only in finite blocks implies that these integrals here must be replaced by sums, simply. Okay, so sums instead of integrals actually provide a result that is different. Okay, this is it. Calculation is really simple. Instead of a distribution of the form P of epsilon, we assume a distribution that has the same functional dependence on energy as before. It is an exponential. But instead of energy, we use n times h_n, in which n is 0 or 1 or 2 or whatever, is an integer number of blocks h_n. So the integral over energy must be replaced by a sum over the index, okay? So you remember in the average that we performed before, we need the integral of P that is in the denominator, okay? And then we need the integral of energy times P, okay? So we perform the integral on P first by replacing the integral with the sum over n. So what we do is we sum this. P0, and then we have 1 e. Theta is the elementary block times beta. Okay. And this sum is easily done. It provides P0 over 1 minus e to the minus theta. Okay. Then we need the numerator. And the numerator is energy times the distribution. So energy is NH_n times the distribution. So we have another infinite sum of this form. And there is a trick. If you take the derivative with respect to theta, you find immediately that the numerator is this. So that the average is the numerator divided by the denominator, and you find h_n divided by exponential of theta minus 1, that is exactly the expression of the average energy used by Planck. Okay, so qualitatively the calculation is straightforward. Instead of integrals, we use sums over integer blocks. But due to that, the result is different. From the conceptual standpoint, the assumption that we are going with finite blocks is completely arbitrary at this stage of the analysis and must be justified. Okay. Observe that historically, the solution of the black body radiation problem came before the solution of the paradoxes of the photoelectric effect. So the Planck constant was extracted from the photoelectric effect. Then it was used by Planck in the analysis of the black body radiation, in the hypothesis that the energy is made of finite blocks, so we may say the energy is quantized only at the moment of being exchanged between the electromagnetic field and the black body. Okay. On the same line, we shall see in the next hour goes the solution of the photoelectric, of the paradoxes of the photoelectric effects. It is still based on the description of the energy of the electromagnetic field modes as individual finite blocks. Okay. The difference is that the assumption that is necessary to justify the photoelectric effect is that the electromagnetic field must be described as finite blocks not only when the energy is exchanged between the electromagnetic field and the black body, but always, also when the energy travels in space. Okay, so these small pieces of energy that travel in space and carry the electromagnetic radiation, as you may imagine, are those that are called photons. Okay. So we shall see it. Now we take the intermission, but in the next hour we shall see the explanation of the photoelectric effect in terms of photons. So we shall see that the description of the electromagnetic field as a superposition of waves can also be replaced with a description in which the electromagnetic field is described in terms of particles, very special particles, but in terms of particles. So we stop now for 10 minutes and we shall resume at 5:40. We'll start now. After completing the description of the problem of the black body, and we proceed with the explanation of the photoelectric effect. The explanation was given by Einstein in 1905, and it was expressed as follows: the transfer of the electromagnetic radiation or energy, is quantized. To better specify this sentence, we must say that we start with the general electromagnetic field. Then we split This is in vacuum. Then we split the electromagnetic field into by the Fourier analysis into a set of monochromatic waves, each wave with its own frequency, and we call them modes, and each mode has an energy. Okay, this is classical electromagnetic theory. The hypothesis by Einstein was that the energy of each mode of the electromagnetic field is the sum of an integer number of energies. Each one is the quantum of energy called h-ni. So in this way, we can view the transport of energy of the electromagnetic field as carried out by identical objects that are called photons. Each mode is made of an integer number of photons, and the energy of each photon is equal to the product h-ni. Given that, we can explain the photoelectric effect by stating that when the photon interacts with the electron of the cathode, the electron may absorb energy from the photon. It may also absorb 100% of the energy of the photon. If that happens, the photon is destroyed. It doesn't exist anymore. It is annihilated. Okay? So, this explanation shows why the blocking voltage in the photoelectric effect was related to frequency, because the frequency of the electromagnetic mode multiplied by the Planck constant provides the energy of each photon. Okay. In other terms, when we increase in the photoelectric experiment, when we increase the frequency of the radiation, we increase the energy of the photons, so that the blocking voltage increases. Instead, when we increase the intensity of the radiation without changing the frequency of the photon, what we do is just we increase the number of photons that are in the field. So the number of photons is larger, and if each photon extracts one electron, the number of electrons that are extracted from the cathode becomes larger, so that the current becomes larger. So this is easily explained in this way. But since we are not changing the energy, the blocking voltage does not change. And this explains completely the photoelectric effect. It also explains why the curves, you remember in the second experiments, the curves intersected each other. Let me go back. Here. I don't rotate the... You see on the right, the curves intersect each other. Why? Because in this type of experiment, we are keeping the intensity constant. Okay? So if we increase the energy, then if we increase the frequency, we increase the energy. Okay? In order to keep the intensity constant, we have to have fewer photons, sorry. they're more energetic, but their number is smaller. Okay, so this is why the curves intersect. Oh, it is written here. Okay. They intersect because the constant intensity is given by more energetic but fewer electrons. Now we have immediately another issue that is an automatic follow-up of the explanation by Einstein of the photoelectric effect. If we describe each mode of the electromagnetic field is a collection of identical particles, the photons, and each particle has some energy, well, if we complete this description in terms of particle, then we should also think that these particles have momentum. Okay. So the idea is there another experiment that may show that photons, beside having energy, also have momentum? Yes, the answer is yes. And the other experiment actually is one of those of the list, of the original list, that I'm not going back so many pages, but you remember at some point in the list, we had an experiment that was an item that was called the Compton effect. So let's investigate what the Compton effect is. It is described by this figure. We have a block of material that is the rectangular gray region inside. This material is dielectric, so that the electromagnetic radiation can cross through it. Okay. And then we have a monochromatic radiation coming from the left. It is indicated by the dark arrows coming from the left. And this is a monochromatic radiation and also planar. The equal phase surfaces of this radiation are planes. These planes are normal to the direction of propagation of the radiation. They are also normal to the page. So these black vertical lines parallel to each other are the traces of the equal phase planes of the radiation. So these planes propagate from left to right, and this radiation impinges on the material, and some of it comes out from the other side. So you see that from the other side we have these gray arrows that describe the radiation that has crossed the material without being perturbed. Some other part of the radiation interacts with the electrons of the material. And one effect that is expected is the following. if you have a radiation with some given frequency, and this radiation interacts with an electron in the material, it may be able to force a vibration of the electron with the same frequency. So the electrons of the material will be subjected to besides the action of the nuclei that still continues, of course, they will be subjected to an extra force due to the electromagnetic field incoming into the material, and these electrons will start oscillating. And of course, they will be forced to oscillate with the same frequency of the radiation. But, as you remember, electrons are charged. So you have a set of charged particles that are oscillating, so they are subjected to accelerations, and they will emit radiation. Now, the electrons in the material do not have any privileged direction. Okay, the orientation of the emitted radiation by these electrons is arbitrary. So all electrons, these electrons will emit in all directions. So the electrons will act as little antennas. They will emit radiation all over the space uniformly in all radiations because they don't have any privileged direction. And what one is expecting is that since the forcing radiation is monochromatic with a specific frequency, all the radiation emitted by these electrons will also be monochromatic with the same frequency. So eventually what we expect is we start with the material, we put the radiation coming from the left, some of it will come out undisturbed from the right, but in addition to that we shall also have a spherical wave emitted by the material, and this is indicated by the circles and by the white arrows. So we shall have a spherical radiation also in the direction normal to the page. And this radiation must have the same frequency as the impinging radiation. Okay, this happens not exactly like that, but this happens, and we can measure the properties of the emitted spherical wave, and we can place a measuring equipment at some position. So you see on the right there is a direction and then there is phi. Okay, we can place a measuring equipment in the position of the letter phi, okay, and measure the properties of the emitted spherical wave. The result is, in fact, that we find a spherical wave. So qualitatively, the description is correct. However, we do not find a radiation whose frequency is always the same as that of the impinging radiation. We find that the emitted spherical wave has a frequency that depends on the angle. When we measure with the angle phi equal to 0, that is aligned with the radiation that comes out from the right, we find exactly the same frequency of the input radiation. But when we rotate up or down, so when the angle increases, angle phi increases, we find that the frequency decreases. So this is an anomaly. The anomaly is that we don't find the same frequency when we change the angle, but we find a different frequency depending on the angle. This anomaly is called the Compton effect. And this effect cannot be explained using the electromagnetic theory or the laws of classical physics. On the other hand, the phenomenon can be explained by assuming that the radiation is made of photons. So the impinging radiation is made of photons that have all the same direction, that is horizontal, and the same frequency, because it is a monochromatic planar wave. And also assuming that the radiation has a momentum. If we put together this information and described, as we shall see in a minute, the interaction of the photon with the electron as a collision of two particles, we can explain the Compton effect. Okay, so the calculation is relatively heavy, so I shall just provide you with the hypothesis and I shall show you the conclusion. Okay. The arrangement is that we shall first identify the expression of the momentum of the photon, and then we shall set up a calculation in which we have the collision between the photon and the electron. There is one difficulty. This is the reason why I'm not going through the calculations, that we must use special relativity. The reason is that in order to detect the effect, the frequency of the electromagnetic field must be very high. Otherwise, the effect is so small that it's impossible to detect. If the frequency of the photons is very high, their energy is very high. But when the very high and very highly energetic photons collide with the electrons, the collision is such that the electrons start moving very fast. So that we must use also special relativity to describe the motion of the electrons. Okay, this is the only point here in this class where we must use special relativity, but I'm not going through the calculation. I was just stating the starting point of the analysis. So the only thing left is, how do we express the momentum of the photons? Okay, the momentum of the photons actually is easy to express because the electromagnetic theory is already relativistic. It fulfills the prescription, the invariance prescription of special relativity. Okay. So if one calculates the momentum of the electromagnetic field starting from the Maxwell equation, one finds that the momentum is the energy of the electromagnetic field divided by C. So we simply take the same result for each individual photon. It is seen here in the formula. We know that for the individual photon, the energy is h-ni. When we use the expression of momentum that comes from the electromagnetic theory, the momentum of the photon is the energy divided by c. Now, the energy is h-ni, and you remember that the definition of the wavelength for a radiation is such that the product of the wavelength times the frequency is equal to the speed of light. So we replace c with the product lambda times c, and then we cancel the frequency, and we have that momentum is equal to the Planck constant over the wavelength. Okay, so this is the momentum of the photon in modulus. Okay. Before we move from scalar quantities to vectors, we introduce the so-called reduced Planck constant. That is, you know it already because we have used it in the crystals. It is h bar, that is defined as h over 2 pi. So for the expression of energy, instead of h-ni, we can alternatively use, instead of h, we use 2 pi h bar, and 2 pi ni is omega. So energy is h bar omega. And similarly, for momentum, we remember that momentum is given by h over lambda. H can be written as h bar 2 pi. And lambda over 2 pi is the inverse of the modulus of the k of the wave vector. And this can easily be transformed into a vector relation. So we have that P as a vector is equal to h bar times k. You see, this is exactly the same expression that we have been using for electrons, but in the case of electrons in a crystal, P is the average momentum, okay? Here it is just the momentum of the photon. Now, in order to describe the collision of two particles, okay, we must remember that if the two particles are isolated, so they are interacting only between each other, but with no other body, and this can be done. We can consider that the collision of the photon with the electron is a two-particle collision. That is, all the other particles are far away and they do not interfere with the collision. So in the collision, we must impose the conservation of the total energy and the total momentum of the particles. Okay. This is not obvious because the total energy also includes the potential energy. That means that in principle, in order to completely perform the calculation, we must introduce also the potential energy that describes the interaction of the photon with the electron, okay? On the other hand, we may consider a simplified picture in which we consider only the asymptotic conditions of the collision. That means we consider the collision very early in time so that the electron and the photon are far away from each other, so they are not interacting very much. then we neglect all the time that is necessary for the interaction, and we consider them again much time after the interaction is finished. So when they are again far away, okay, so that the interaction is very small. In this case, of course, the description is poorer, okay? We do not work out all details in this case, but if we consider just the asymptotic conditions of the interaction, we can neglect the potential energy, okay? Because the two particles are always very far apart from each other. So the conservation of the energy eventually reduces to the conservation of the kinetic energy only. And this is much easier in the calculation, okay? So we lose something, we lose some detail of the interaction when we consider just the asymptotic conditions, but we can perform a much easier calculation, okay? So it is conservation of kinetic energy and conservation of momentum. Another issue is that this is something that is already given in the elementary classes on mechanics. When you have a two-particle interaction, essentially you can assume that the motion of the two particles stays always on the same plane. So we start by assuming that the two particles belong to the xy plane and that the velocity, one particle is not moving. The electron initially is not moving, is in the origin. And the photon is moving on the xy plane. So the initial velocity is on the xy plane. So we can treat the problem as two-dimensional. The particle will never come out of this plane. So now we have the equations. Probably there is a figure somewhere. Let me check whether there is no figure. Okay, so let's consider the conservation of momentum first. Okay, so we said before the collision, the electron is not moving, so we can place it in the origin. So before the collision, the momentum of the electron is 0. Then for the photon, we can assume that before the interaction starts occurring, the velocity of the photon is parallel to the x-axis. So the momentum will have one component along the x-axis and 0 component along the y-axis. Okay, so the component of momentum of the photon with respect to the y-axis is in the second equation on the left. It is h(n) over c. Okay. Then we must consider that during the interaction, there will be a change of energy between the electron and the photon. Okay, you remember in the photoelectric effect, there is a total absorption of the energy of the photon by the electron. So the electron destroys the photon because it absorbs 100% of its energy. In this case, we must assume that the electron that before the interaction is not moving, after the interaction will be moving. Okay, So if the electron initially is not moving, so the kinetic energy is zero, and when the interaction is finished, the electron has suffered the collision and is moving, the electron has some kinetic energy. On the other hand, the total kinetic energy of the two particles is conserved. So if the electron has increased its own kinetic energy from zero to non-zero, the photon must have decreased its own energy from non-zero, from some value, initial value, to some other smaller initial value. But on the other hand, the energy of the photon is h-ni. So the energy of the photon before the collision would be some h-ni. After the collision would be some h-ni prime, with ni prime smaller than ni. So the photon has lost some energy, not 100% of its energy, okay? So that its frequency has decreased. When we continue with the analysis of the momentum conservation, we have to go on the right-hand side of the two equations. The second equation describes the conservation of momentum along the x-axis. And the second equation in the momentum block describes the conservation along the y-axis. So for the x-axis, we have that the momentum of the component of the momentum of the photon in the x-axis direction will be the energy h-ni prime over c. That is the modulus of momentum times the cosine of phi. Phi, as you remember, is the angle between the orientation of the motion of the photon after the collision and the x-axis. And then we have to add the momentum of the electron, that is mass times velocity, mu times the cosine of psi. Psi is the angle by which the electron moves away with respect to the x-axis, okay? When we go to the y-axis, of course, we have 0 on the left. Then we have that the component of the photon momentum with respect to the y-axis will be h-ni prime over c times sine of phi. And that of the electron will be minus mu times sine of psi. Of course, there is a minus because if the photon is deviated up, the electron must be deviated down because the total must be zero. The total of the two momenta must be zero, and vice versa. The first equation is that of the energy. Okay, this is a little bit trickier because in relativity we must consider the rest energy. So on the left we have the initial energy of the photon h-ni plus the so-called rest energy of the electron, that is m0 c squared. On the right we have the energy of the photon after the collision, h-ni prime, plus the energy of the electron, and the energy is the relativistic mass m, that is different from m0, times c squared. The relativistic mass is defined in the previous page. Here, the relativistic mass is equal to the rest mass divided by the square root of 1 minus the velocity of the electron squared divided by the speed of light squared. Okay, this is what makes the calculation complicated. So after a long calculation, we can eliminate psi. The object of the calculation is to eliminate psi and define the variation in the frequency of the electron as a function of angle phi. That is exactly what we detect in the experiment. You remember, in the experiment, we detect the frequency of the photon, or the variation of the frequency of the photon with respect to the initial frequency, as a function of the angle by which we measure the radiation. Okay, so qualitatively, by this calculation, you understand that by eliminating the other angle, we end up with a formula that is due to Compton. And this formula is this one. It is better expressed in terms of the wavelength. Lambda prime is the wavelength that corresponds to ni prime. Of course, lambda prime is larger than lambda because ni prime is smaller than ni. So the variation in the wavelength is equal to 2 times some constant wavelength that is indicated below. L lambda c is h over the rest mass of the electrons times the speed of light. It is called the Compton wavelength. And as you can see, it is rather short. It's some units 10 to the minus 10 centimeters. And this Compton wavelength multiplies the square of the sine of phi half. Okay, so when the measuring equipment is aligned with the incoming direction, we have phi equal to 0. So the sine is also equal to 0, and there is no change in lambda or in the frequency. So the frequency is the same if we measure aligned with the incoming direction. If we go on the opposite side, so we measure the radiation that is reflected, then phi is equal to pi. So the square sine of pi half is 1. So when we measure on the opposite side, that is on the same side from which the radiation is coming, the effect is maximum. And you can see immediately that even in the case where the effect is maximum, the variation in the wavelength is pretty small, is 2 times Lc. Okay, so this is why the effect is so difficult to detect. So in order to detect reasonably well the effect, the original wavelength must be small itself, because in this case, the difference lambda prime minus lambda is compared with a number that is also small. So the relative variation of the wavelength is can be detected relatively easy. Okay, so lambda must be very small. That is, the frequency must be very large. So the experiment must be made using the X-rays, at least, in which the frequency is 10 to the 18 Hertz. Okay, but such a frequency is so high that the energy of the photon is very large. And the energy of photon that is very large kicks the electrons so strongly that the speed acquired by the electrons is non-negligible with respect to the speed of light. And for this reason, we must use the relativistic expressions for the dynamics of the electrons. Okay, this is the reason why we must do that. On the other hand, the outcome is that this formula here fits pretty well the experiments. Not just qualitatively, it fits very well considering also the numbers involved. So that means that the hypothesis that we can describe a monochromatic radiation as a flux of particles having not only the same energy but also the same momentum is reasonable. Okay, and that the picture of the electromagnetic waves as photons is acceptable. So this introduces what is also called the duality between particles and waves. Let me go back to the original list. Okay, so we have examined the stability of the atom, the spectral lines of the excited atoms. We did not give an explanation for the stability and for the spectral lines, okay? There has been an explanation for the photoelectric effect. There has been an explanation for the black body radiation. And there has been an explanation for the Compton effect, but for the moment they are based on, so to speak, independent assumptions. Okay. Now we must consider the Hall effect. The Hall effect is completely different. But at some point, if I remember correctly, we have introduced somehow the effect when we were discussing the sensors of the magnetic field, okay? So I don't think it is worthwhile repeating this issue. In essence, the Hall effect seems to imply that there are materials like p-doped semiconductors in which instead of having electrons that carry the current density, we have positive particles, okay? We know that this is true in some sense, that in semiconductors that are doped of the p-type, it is more convenient to use the holes as carriers, okay, because the dynamics then is identical, apart from the symbols, to that used for the description of the electron dynamics, okay. Obviously, in solids, it is the electrons that carry the current, but the description is equally well carried out in terms of holes, okay. So it is not necessary for the moment that we consider the Hall effect. The last issue is the diffraction of the electrons. The diffraction of the electrons was actually used as a method for providing a physical meaning to the wave function, okay? So I have a movie somewhere that shows the diffraction of the electrons. So I'm not sure that I'm able to find it, but give me a few minutes because I just want to show you the movie. Okay, I found the movie, so I must be able to share that video. Nope. Looks like it is more difficult than I expected. I'm not able to do this. So we stop here for tonight and hope to be luckier on Tuesday because it is a very interesting video. It shows actually the first case in which people have indeed succeeded in producing the interference of electrons, okay? So it's something that you should be able to see, but I don't know how to share the video. So I'll study the issue over the weekend. Okay, so for the moment we stop. Thank you very much.